Hope you guys are doing well. So, continuing on our journey, today we will try to understand uh, what. Uh, like basically, we would be understanding how OS manages the main memory, right? So, we all know RAM is a very important part, right? So, we'll try to understand that and then we'll go on from there. So, before we go with that, a little brief introduction, a brief recap. So basically, our programs are stored in the SDDA or the SDD, right? These are basically the secondary storage devices that we have. These are stored in the format of exe, right? Basically, something that is uh, uh, like an executable file, right? So the moment we double click on this, what happens is a process control block is created, right? Now, once the process control block is created, now what the process is then put in the main memory, right? So this is from where the CPU is going to read data, right? So remember, this is random access memory. It is a very fast memory. It is all on-built on the. It is in very close vicinity of the CPU, right? So CPU is going to protect pick processes from here. For example, process one, process two, process three. Now this will happen based on a some scheduling mechanism that is done by the scheduler, right? Now the moment, so what happens is, so each process will get its own memory block allocation by the operating system, right? So the moment it comes on the RAM, each process will get a specific sandboxed environment. The sandbox is basically something that is isolated from the other, right? Only with respect to that process. So this is done by the operating system, right? The next thing that we have is, now basically there are two major areas of memory blocks, right? So when you have a process being added to the RAM, so each process will have the two memory blocks, right? Basically that is going to be the RAM heap and stack. Now we'll see what the heap is. So basically the stack is limited in size, and once the work is done, memory is released, whereas heap, it is unlike the stack. It needs a mechanism for dynamic cleaning, right? We'll see that later on. Now then let's come back to something called as the virtual machine, right? So whenever we install a program, right, we need to install the virtual machine as well. Now the virtual machine consists of an engine and has access to the memory, right? Now because it's a virtual machine, the reason this is what it's called as virtual is basically something that is not in reality. It is basically a software emulation, right? Or however, it will be using the physical CPU that is installed on the computer, right? So you can classify virtual machines into two types. One is a full computer, basically a system virtual machine. You can install an OS. It will have a CPU. Remember, these are all software emulations, right? However, it will be installed on a machine, right? On a physical device. A physical device will have hardware limitations. The second is basically where you have a single process running, right? So this is nothing but where you have PVM or GVM or whatever virtual machines that you have. The single process virtual machines, basically these are mini computers, but they are only they are not present in reality. It is a software emulation. Now it is called as a virtual machine because what this engine is going to do is, so this is engine is going to produce the executable, right, that can be executed by the CPU. So since it's working like the CPU, we say that this is a engine, right? Or we say that this is a virtual environment. Now RAM is basically instruction that the CPU can, so CPU can only read from the RAM, right? So for any file to be executed first from the this is not ROM, this is basically HDD. From the HDD we have to move it into the RAM, right? So this is not ROM, this is not ROM, this is secondary devices, right? For example, your HDD, or even you can say SDD, right? So if you want them to run, first they have to be loaded into the RAM. The CPU will then um, run that process. Now this process, VM virtual machine job is basically to provide the format. Since it's going to, a CPU needs a certain format, right? So from the HDD it can come into the RAM only if it has a certain format. That certain format is basically generated by the what do you say, the virtual machine, right, or the VM. So VM is going to have that CPU generated format. Then it is then the OS will, so once you double click it, the OS will then put it in the process queue. Now based on the scheduling algorithm, the CPU will be able to schedule it. How does, so the main question that comes is, how does the memory allocation takes place? Or remember, CPU has no role in memory allocation, right? It is all done by the uh, CPU. Does not have anything, right? CPU is just uh, CPU is only for using it or working on or the execution, right? So CPU, there is no role of CPU coming into place, right? So the all everything memory allocation or any other work, that is basically done uh, by the operating system, right? So now how does operating system work? So this is a CPU, right? CPU has something called as an, so this is a CPU, right? So CPU has something called as an address bus, right? Remember this address bus um, is, so this address bus can closely is in close vicinity of the ROM, right? The read only memory, or sorry, the RAM, the random access memory. The ROM is for storing boot programs. For example, one of them is boot. Yeah, when system boots, right, you need to initialize the hardware, right? So that time uh, that is provided by the motherboard manufacturing company. So that is never erased off. Random access is basically or RAM is basically when you want to do some random accessing, right? So now what happens is, now CPU has something called as an address bus. Now remember, these addresses bus are 16-bit in nature. So now what we do is, we do not give the exact physical address, right? We divide the address into two types. One is something called as virtual addressing. So we have something called as an address generation that takes place, right? So CPU can only generate logical addresses. Now CPU will have something called as an address bus, right? So if this is a 16-bit CPU, then I can generate about 64K addresses, right? Now remember, this address bus or the CPU is connected to the RAM, right? The catch is the RAM is will be in GBs, right? So it will be 2 GBs, 4 GBs, and 8 GB, and we are still in KBs, right? So this is nothing but an address wastage, right? The remaining bus, or if you are accessing only 64K memory locations out of 2 GB, you are wasting a lot of data, right? So what this, to avoid this, we do something called as we don't give the, we generate a virtual address, right? So what we say is, actual address is the logical plus the relative address, right? Now how this management is done, this is done by something called as the MMU, right? Remember how, so how is the logical address comes to the CPU? Remember, CPU cannot produce anything. CPU is basically idle, right? So this logical address, the moment we create a process and put it in the RAM, right, there is a program counter that is present in the process. Now that is nothing but the logical address that is given to the CPU, right? Then CPU then passes it to the MMU, which is nothing but the memory managing unit, and then that is linked to the RAM, right? So this is how the address is basically generated, right? Remember, to access the RAM, we need the actual physical address, right? So the actual physical generate is generated by a combination of two. You do something called as logical plus relative. How does CPU come to know the logical address? Remember, program counter is associated with each processor, right? So the logical address is stored in there. Now once this is done, so once we have the address, right, so now the thing is, so right now we were only so for the CPU to access, the CPU needs the address, so that part is taken care of. Now we need to understand how is the process going to get allocated in the, like, what memory operation is the how is the memory being allocated to the process by the OS, right? Now there are different methods using which memory can be allocated. First is the contiguous block allocation, right? Now whenever you allocate a contiguous block, remember, this is limiting our memory utilization, right? You will not have one processor running at a time, right? You will be having multiple processors running at a time. So this is not a very good format, right? So what we do is, we, even paging alone itself is not a very good thing. Segmentation is basically dividing the memory into different blocks, right? This is nothing but something called as virtual, right? Remember, that is not memory as a whole is a single thing, right? But what we do is, we do something called a segmentation. Basically we divide memory into different blocks, right? One is heap, stack. So basically that is nothing but a virtual concept that is not happening in reality. So in reality, what we would be using is something called as page segmentation, right? So we'll be using both paging and segmentation, right? So although we have so many methods, but the most easiest and the efficient way is paging plus segmentation. I know what. So segmentation is basically nothing but divide segments, right? You break down the memory block into different segments, called as segments, right? So for example, you have stack, heap, and text, right? Now this text is something that is very important, right? We will see where or how we will be utilizing this text, right? So now what happens is, remember, so the memory allocation will happen at random, right? For example, if I have this block available, then it might OS might give this to Discord process. So or if I have, for example, now see this Chrome processor, right? It gives, so it is not always that the contiguous memory allocation is being done, right? But then we say that in array, right? So we say, so this specifically is when we are using arrays, right? We say, oh, array is contiguous allocation, right? Remember that allocation is nothing but it's nothing but a, it's not the actual, right? It's a virtual memory that we are talking about. That is not the actual representation. It's just a way for us to virtualize or to idealize how the memory is going to be allocated. Now the next thing that we are going to see is basically something called as, so basically, as I said, uh, it may happen that random locations may get random memory blocks, right? So some may get this, some may get this, right? So this is happening at random, right? It's very random. One cannot predict which block is going to be allocated to which process. Now whenever we come to node, right? So for example, node, so for example, no, so this is just an example, right? So node may be given this block, VS Code might be given some other block. Remember, everything is the process, right? Now this is a very important criteria, right? What happens now when RAM is full, right? Yeah, if you have too many processors running, remember RAM is very limited, right? So RAM is only limited, and it's generally 2 GBs, 8 GBs, or 4 GB, right? So or 16 GBs, like the most modern may have 16 GB one. This is very limited in size, right? So what happens is, so when this when the OS comes to know that, oh, RAM has become full, what it does is it add an additional layer to it from the disk, right? So this is basically the HDD and SSD. Remember, these are very slow memories as compared to the RAM. So the drawback is, whenever you're trying to access data from here, you'll be losing a lot amount of speed, right? And the next question comes is, why stack faster? Remember, stack allocation is directly done by the OS, right? There is no, so in memory segmentation, when we are doing, so whenever we divide the block into different size, right? We assign different blocks, different pieces of code, right? So remember, stack memory is always segmented, right? The reason for, sorry, this is a part of the segment, right? The stack is considered to be a faster memory. Is the reason behind this is the OS can directly allocate the stack, right? There is no middleman required. Whenever you are accessing heap, yes, you need a middleman such as a memory allocator or any other uh, uh, so you need a middleman to dynamically allocate that memory, right? Because this heap can be increased or decreased depending upon even if the process has been executed, right? Like if you do not need that memory, the memory or the garbage collection has to be manually done when you are using heap. In case of stack, it's automatically, right? If anything is done working, it's popped out from the stack. Now then let's see, like, do we, why does the size of the variable matter? Like if you say that we can add HDD and SDD as well, that means we have infinite amount of memory available, right? But then that is now how what we want our programs to run, right? Remember, it's a job of the so this issue arises, so in whenever you have a statically typed language, right? For example, that has a compiler in it, for example C or C++ or Java. Now the engine is capable itself to produce a code, or a code that is can be run by the CPU directly, right? For example, it may consider some instance like move a register be something like that. So that is directly produced. But then when you're dealing with an interpreted language, yeah, this does not happen directly, right? You need to add, first is you need to do the type checking at runtime. That is a very big headache, right? And second thing is you need to make sure that you need to add extra blocks to the memory, right? For example, remember I was talking about there is some extra spaces in the memory, right? So in whenever there is a process, right? So there is a um, yeah, this stack, we have this extra extra space available for text, right? Now what this extra text is going to contain is basically in interpreted language we need to specifically mention. So those are dynamically typed, right? Those are understood at runtime. So then we need to allocate extra blocks, especially mentioning that it was a string or it was an integer that is being used, because there is no since because if we don't do that, then the OS would not know how much memory should be allocated, right? So because if you have a variable, say in 32, right? So say if you say in 32, the 32 basically mentions the size, right? So remember, this becomes very critical when you are in interpreted language because they have lots of overhead. However, although they are having lots of overhead, still JS is used, right? Because it has other advantages, other famous libraries that are written in JS, right? Um, so basically JS will sometimes it will add an exclamation mark with number one, right? It does that automatic conversions, right? That is a big headache whenever you're using a dynamically typed language, for example. So that is why TypeScript came, right, to mention that type, so that we are using reducing little bit load from the interpreter, or thereby enhancing the speed, right? So mentioning the type is. So that is why we say type checking is always needed. Type checking, because at times for dynamically typed languages, especially like JS, right? It's basically going to reduce uh, what do you say? It is going to catch bugs early. Second thing is it is going to reduce the overhead, right? There is no impact on directly performance because the types are erased, but then still, because that type checking has been done, it indirectly is going to boost the performance, right? We can optimize the GIT much better, right? We need GIT or the just a JavaScript in time compiler just to produce the CPU codes, right? I mean the thing that can be understood by the CPU. So adding additional facilities onto the interpreter is not a very good way of writing code, and hence we use TypeScript because it uh, first of all is going to mention the TypeScript at runtime, and that is going to help us to catch runtime errors, right? And then the other is it is going to reduce little bit of overhead. So hence TypeScript is a very hence we prefer mentioning the types, right? Hence uh, uh, um, what do you say, hence having uh, mentioning the type or the size is very important, right, whenever you are using any language, because remember RAM is always fixed, right? The more OS allocates for you, uh, uh, the more issues you are going to have. So now there is something called as paging, right? So paging is basically a concept by which the OS allocates memory, right? Now it is not only paging, it is paging plus segmentation, right? So there are drawbacks as well, there are speed limitations as well, because what if a page has to be taken out and the so if you see that way, uh, the RAM only, or the OS only loads those pages into the RAM that are needed at that moment. If you do not need that instruction right now, it won't be loaded, right? So basically we are doing something, we are optimizing this bit so that whatever is used, just load them so that the RAM is still available for other processes that need the memory, right? So it's basically paging is for uh, avoiding unnecessary wastage, right? Avoiding, because RAM is a limited resource, remember RAM is very limited, right? So we don't want any wastage of RAM to happen, and CPU can only read the RAM. So if wastage of RAM occurs, then paging basically is a feature to increase that efficiency. So that is one Basically, paging ensures that we only need memory if a program is too big, right? So don't load the entire program, right? That is going to because when you are using a CPU, right, there are multiple programs that are being run in the background, right? So you don't want more processes to be running, or don't want the entire RAM to be wasted. So whenever it says disk full, that means RAM is full, right? So you need to kill some pages, or maybe you need to. Although OS is very efficient, right, in doing this, but then still, this especially happens when you have so in Windows OS, this is a very major concern, right? RAM. So, but then if you use something called as a Mac OS X, you hardly face any lag issue, right? Because the OS is designed in such a way to be more efficient, right? So whichever load you put onto the lamp, the Mac OS never lags. That first is basically the way paging is done, right? Demand paging is a really good concept that is done by Mac OS, right? Now Windows doesn't have that. Basically, only what things are running, those are being done, right? But however, so Windows lacks that paging effect, right? Because if you so you won't be loading everything, right? We'll be loading small chunks, right? So if you try too many apps, so switching between those uh like swapping is going to be an issue, right? So hence Windows so I'm trying to check if Windows has demand paging, because Mac OS has that feature, right? Even Windows has, but then first is the hardware reliability, right? So Mac OS is very tightly coupled because the hardware as well uh, they manufacture, right? Second thing is in Microsoft manufactures Windows, however the hardware is from some other company, right? Now it ultimately boils down to that thing, right? Uh, First is how it's designed, right? The chips, the hardware. The other big disadvantage that we have is basically we have memory and paging, right? So Mac OS does something called as compressed memory before paging. It does smart prioritization that there is no memory leaks happening, right? So memory leak is going to happen is when suppose this is a window node process, right? Now it's trying to access a memory of Chrome, right? So then that is nothing but a memory leak, right? Now Windows must so Mac OS has one GPU and one audio driver, right? First is the how the paging occurs, right? So in Mac OS we have something called as smart app prioritization, right? So uh, uh, that is a very big advantage, right? Now we still use HDD in Windows, right? However, Mac has to so basically hardware. That is the second thing is the hardware, right? So hence, if you see Mac OS does not or never will lag as compared to Windows, right? Because it only is going to do something called as demand paging. So uh, yeah. So what does OS do is it kind of does that paging system, right? So you do not load the entire. If it's a big, you load it in pages, right? So but then how to remember the next page is basically you have something called as the offset address, right? So using which you can have the next program next page available, right? So the whole thing what I was like what I'm trying to say is uh, the OS does not allocate contiguous blocks, right? It can be any random blocks. So basically, whatever block is free in the memory, it will be allocated, right? So, and there is no specific rule of how the blocks are allocated. Whenever you deal, we say array as a contiguous. This contiguous location is basically when you are respecting to virtual memory at a very virtual memory level concept, right? Initially, it might be anywhere. If you see in the hardware, what is going to happen is the frames are going to have a reference to those indexes, right? So internally you cannot physically on the hardware they will be stored anywhere where there is a empty space available, right? So now each process is going to get a specific set of memory, right? That is given allocated by the OS, right? um, uh, Now, so the process, so that memory allocation will not be contiguous. It can be a breakage of parts here and there. That is internally it has a pointer to each of those, right? So every process has a pointer to each of its how do you say, each memory location, right? uh, so JS is because it has that uh, the JS is widely being used is because um, there are something called as first is JS can be understood by the browser, right? That is one of the very big advantages why JS comes in with that handy feature, right? If you are using Python, you will have to do something to convert that Python code to JS, right? Or something, some that. Second is the library support is just massive, right? Now, although browsers are very optimized, right? So RAM is mostly abundant. Although so JS does not have that those bottlenecks whenever you're doing IO rendering, right? Heavy computation can be offloaded. You can do at backend or on your physical server, right? You don't want that heavy computation to be done on the user's end, right? So um and the other is basically so TypeScript is like a layer on JavaScript, right? So hence we say nowadays we are more towards TypeScript, right? Because that we are trying to eliminate that load on the runtime, right? To check the type at runtime. So because if you already have that component, I believe that you can generate that CPU code. You can predict the memory layout more easily. You can avoid extra. Yeah, so extra memories. Remember that string, right? That is a metadata, right? So you need even that will be allocated into the memory. So hence we are now moving towards TypeScript because of those disadvantages. Um, yeah, you need to track that type, right? So the memory also will have that integer int inside that text, right? That is a metadata, right? There is a specific in the process control block in the memory. You have segment, you have heap, right? So heap, I said again, it's done by memory allocator, so it's already slow as compared to stack, right? Anything that comes in a stack is just done by the OS, right? So it's very easy to just push it and pop it. However, if you are using heap, even to remove it, you have to use the memory allocator. The second thing that comes is uh, there is a field called as text, right? That text is nothing but the metadata. For example, for type dynamically type interpreted languages, you must mention that because only then will the OS know how much memory has to be allocated. Else we don't. So the registers are on chip, right? Based on the CPU. So a chunk of memory is given, right? Uh, But however, we need to understand, right, how much. Yeah, we already know the compile time, right? So the program is just you going to use the raw memory. So then now if you are saying that the OS allocates, also there is a specific size how much allocation that is done. For example, if it's a Mac OS, oh wait, there is, I guess there is a uh, each OS has a specific. Wait, I looks like it looks like uh wait, uh, how does OS do? Okay, uh, there is a very specific way of to do that. Memory allocation in different operating system. Like for how each process, how much is the uh, I guess it's not very huge. It's something called as was in the 4 kb range, I guess. Let's check how much memory does this allocate to process. It's very fixed. Yeah, it's very less, right? It's in the kb region because then we have demand paging as well coming in. Is there a guide or something? Yeah, you can even limit out uh yeah, you can limit the memory allocated. There are commands for it, but then it's not recommended. So yeah, statically type will avoid that overhead, right? Those will be there. Uh, so if it's so why do we need the metadata? Why do we have that metadata? The program does not have any idea about what the values type is at runtime, right? Until it checks. The time can be so that is not for the OS. Also, that metadata information is for running, right? Remember, we need to have that. But when we are in process or to go to the process stage, we need that, right? Is that yeah? So when the source code is already written, we know. But in dynamic type, that information is not preserved until we run it. So the process image in the memory has no fixed, right? There is this. Yeah, those that extra information has to be mentioned, I guess. Because whenever you are going to perform arithmetic operation, you need to go back to the ALU, right? So this is for basically for CPU reading, right? The CPU needs to know what's happening there. Mm-hmm. Yeah, basically it needs that size thing. It doesn't care whether it's a string. But for in dynamic leaf, for that size, we need to know the type, right? What is the size of that value in memory? It's basically there is does it perform some computation? So it does not know actual size, but it does. So the OS does know how much memory is allocated to each process, but does not know how much to allocate. If there is, it needs more memory, then there is something called as demand page. Okay, so yeah, it cannot predict how much will be needed. It just that is done actually when the execution happens. Now what is this? Oh, so he's saying that. Um, what about variable? That is dynamic, right? So if the variable value is initialized or something like that. Yeah, if it's initialized only, then it comes in the. So basically, because JS has that feature that you can initialize it later on. I get it now. What it's trying to say. So in interpreted, we don't know what is going to happen when, right? So the moment we need that only, then the memory is accessed. But doesn't the JIT check and the. But if it's doing that, if you already have that beforehand, right? What is it trying to? Okay. This is very common in interpreted languages, I guess. So how does OS know? So how does OS? Oh, when we are interpreting, when we have completed, we already have. Yeah, we already have that code present, right? So you're saying OS loads the inter. Oh, it has to be that executable file, right? So it start okay. So so whenever you're running a language, it's not the code that gets in the in the process. It's the dot executionable file, right? So that is in the interpreter. So the interpreter is going, and then if you need more memory, then something called as demand paging happens. Okay. It's something like this that is going to happen. So OS is basically going to load the interpreter. The interpreter starts running the code. Then also the Google application that we run is already in executable. Then directly process can be allocated, right? A pre-compiled exe. However, if you are running a program, so what if a mobile app, an executable file is needed to be run? Oh, so yeah, so it will be dot. Okay, That is already an executable, right? So whenever you install any app, what you are getting is basically exe. But however, in Mac, we have something called as .tar or .gz. What's that? So it's like a folder. So we need to unpack that folder. And then does it come into like .dz or something? Okay, let's install Firefox. Okay, let's see what is going to happen. Let's see when we install. Let's have this thing. Let's have this thing right now. Let's get rid of this. Let's go to say Fire. Oh, we have to go to App Store, right? So we have to go App Store. Now we say duck by duck. Okay, not let's not go apps. Let's try it from the website. So if we say Firefox, let's click on download. Okay, so it is going to come in a .dmg file. Now what is this file? So let's save this. It will be zipped, I guess. Let's open folder location. The moment I double click on it, oh, so now what has happened is, uh, what is the dragging icon? Oh, this is fire. So mount that is. So when I'm so now, okay, this is basically saying, oh, this is the Firefox. Open. Let's say show package contents. Oh, this is what it is containing. Oh, I don't need to install the cancel. Let's just okay. So right now this is a bundled file. When I click on the bundle, so this is nothing but app feature. So this is like the .app file. This is what it's containing. So yeah, plist and any other. And then when I try to drag it over here, then something should happen. Right. So this is the app. So Firefox is an app download. It's a .app. Let's say just open it. Let's open the app. Oh, this is how the app looks. Oh, I guess so. Yeah, remember when you were doing this? This is the .executable file that is. See, it's now it changed. Now you got all the packages and all. Oh, CPU. We are running the. So executable is something that is hardware independent, I feel. Oh, I guess so dot exe are hardware independent. This is way this is like it's ready to run and yeah. So basically already you have the CPU specific instruction, right? And when we download it, we get the CPU file. They're going to package it. It may be some DG a app, and then we get a pre-compiled binary. Uh, So basically, we are downloading the binary file, not the source code. We don't access it. Yeah. So basically, our app is the thing which you download is not the source. Yeah, even the interpreter is the binary guy, right? So then that is how uh, for language when you run on your local machine, you get that thing. So yeah, as I said, the way OS allocates it allocates memory to the interpreter, not the entire file. When you download something, we are already in the executable or APK or whatever DMG file. So that directly will run into the. It's already executable, right? So it will already run. There is no need to check something on that. And so if I have the executable already, so if I have the interpreter, right? So in other things, I can. There's a specific size for each interpreter, right? So as and when I'm executing that code, if I need more memory, OS is come. If I already have a exe file, then we already know the entire size, right? So OS will allocate that much memory. Like you cannot predict full size. The binary size it can see, and as and when okay, yeah, as in so entire full memory is not allocated. Yeah, that is how. So even if you have a dot app file downloaded or a dot apk, so the moment you need or the moment you start running that application and the moment you need more memory, OS already automatically does that demand paging thing. And why Windows fails? First is hardware architecture relation, right? Why does it lag a lot? Okay. Yeah, what this, it has a very this unified memory, right? One single thing. This is something special, unified. Yeah, chips plus memory and OS, right? So they are finely tuned. Okay, so yeah, I guess that is all for memory management and why we need to be very specific about memory, right? Um, so I guess that is all for this session. Hope you guys liked it. Yeah, so that is why. So we also saw the difference in interpreted languages, right? It's the interpreter that comes in, and yeah, and then as and when we need, so when the interpreter starts executing the code, that is on demand, and then there is a little bit of more overhead because of the dynamic type, right? So that string, even that text has to be stored as a string. So we are using more memory as compared to if it was a in32 thing. And then it has to do lots of work. Even the memory, sorry, runtime check has to be done at that time. So I guess that is all for this session. Hope you guys liked it. And whenever you download an application, it's directly in the exe, right? So it has a certain size. So OS can predict that size, and as and when the OS is running, more memory is needed, more is allocated. That's demand. So yeah, I guess that is all for this session. Hope you guys liked it. I'll see you guys in the next one. Till that time, take care, bye bye, and please subscribe to my channel. Okay, thanks, bye bye.